Hi everybody, this is Mrs. Hanson, and this is a special edition of AP Chem Radio. For those of you guys that are still struggling with some of this thermochemistry calculation business, I'm hoping this video will help clarify a couple points. So the first thing we're going to talk about is Hess's Law. Hess's Law is awesome. Why? The great thing about energy in general is that it's a state function. And what that means is that when you release or absorb energy in a chemical reaction like delta H for a chemical reaction, it's really just the difference between the energy of the reactants and the energy of the products. The great thing is it doesn't matter how you get from reactants to products. Like you can take any random path, really crazy path, doesn't matter. It's the difference between reactants and products. Or you can take like a really straight path, doesn't matter. So that's what Hess's Law, that's why you're allowed to do Hess's Law, is that you can add up like seemingly random reactions, and as long as they, manage to add up to equal the reactants and the products that you want, then it's perfectly fine. So let's look at an example. It says write out the chemical reaction that would be represented by the standard enthalpy of formation for the gas acetylene. Okay, so standard enthalpy of formation is something really specific. It's the amount of energy typically released when you form 1 mole of a substance from its most stable elements. So first things first, we need to write out this reaction. So we're making acetylene, which is C2H2 gas. All right, well, what elements are we going to make it from? Obviously carbon. And the stable form of carbon, its elemental form, is graphite. We learned that in the Hess's Law POGL. Okay? And then hydrogen, which its most stable elemental form is diatomic hydrogen. Okay, and this is standard enthalpy of formation, which means that we're at 1 atm pressure and 25 degrees Celsius. All right, last thing, we do need to put this 2 in front. Okay, so 2 moles of carbon plus 1 mole of hydrogen makes 1 mole of acetylene. All right, so now letter B says, using the 3 combustion reactions below and their enthalpy values, calculate the standard enthalpy of formation for acetylene. So again, it's that standard enthalpy of formation. So what we're calculating is the heat released or absorbed in this process. So we're looking for heat of formation for this by using these 3 equations. All right, now oddly enough, they call these heats of combustion reactions. So you have to broaden your understanding of combustion. Combustion is really when you react anything with oxygen gas from the air. So this is a combustion of carbon in the form of graphite. This is a combustion of hydrogen to make water. That seems really weird, but that is typically, it is a combustion reaction, okay? And this is a more traditional combustion reaction, okay? Doesn't matter. Notice that they can have the label delta H of combustion, but delta H of reaction is fine too. All right, so in terms of Hess's Law, a couple techniques. One, I like to start with sort of what seems easiest, what's found in only one place in all these reactions. So I'm going to start with the acetylene. I see it right here. Let's see, I see it in this reaction down here. But there's 2 problems. One, there's only 1 acetylene in this equation, but there's 2 here. So I'm going to have to cut this in half. But if I cut this in half, I have to cut the entire reaction in half. So this is going to go to 1, this is going to go to 5 halves, this is going to go to 2, and this is going to go to 1. So I'm cutting this in half. The other problem is that acetylene is a product here, but it's a reactant here. So that means I'm going to have to flip the whole equation. Well, that's fine. If it's exothermic the way it's written here, when you flip the equation, well, it's going to become endothermic. So that's when you got to change the sign. So right now it's a negative sign, so I'm going to have to change it to positive. For me, when I have to flip the reaction, I rewrite it. So I'm going to go ahead and take 2 CO2 plus 1 water, makes my acetylene, plus the 5 halves O2. And then I'm just going to scribble this out because I don't want to confuse myself. But I'm going to leave this because that's looking pretty good. Okay? All right, so let's see. I'm going to put a check mark right here because we took care of the acetylene. All right, now what about the graphite? Okay, so I see the graphite here. It's in the right spot. It's on the reactant side. But there's 2 of them here and only 1 here. So I'm going to have to multiply this whole equation by 2. I'm going to take this, multiply it by 2. Whatever I do to the reaction, I got to do to the energy value as well. Okay, so check mark. Graphite's taken care of. Now the hydrogen. Well, there it is. It's on the right side. It's a reactant, and it's got the right number. There's only 1 hydrogen, 1 hydrogen. So I can leave that bad boy alone. Okay, well now we're going to go ahead and make sure that we actually did this right. So what I like to do is circle the things I'm supposed to have. So let's see, there's my acetylene, bam, it's in the right spot. There's my graphite, and it's the right number, and it's on the right side. And there's my hydrogen, okay? All this other gobbledygook better be crossing out. So let's see, 2CO2, it's on the reactant side here, it's on the product side here. Ba-bam, ba-bam, crossed out. 1 water, 1 water. They're on opposite sides, they can cross out. And then 5/2 O2, that's really 2.5 O2s, and 2.5 O2s. So between all this, my oxygens are going to cross out as well. All right, so I produced the reaction I was looking for. All right, from here, it's just a matter of adding this up on your calculator. So 2 times a negative 395.5, or sorry, 293.5, plus negative 285.8, plus 2,598.8 divided by 2. If you did all that correctly, you should be getting an answer of 226.6 kilojoules per mole. And very important, what would be the label for that? That's a delta H of formation standard for that acetylene. Okay, so it's the amount of energy in this case absorbed in order to make 1 mole of C2H2. Okay, so I hope that helps a little bit with Hess's law. If you're doing it right, it should be oddly sort of fun. Okay? All right, now here's probably the more challenging part. Sometimes you guys can, calculate delta H of whatever, and then you have to do something with that number. So here's a classic calorimetry application. It says calculate the final temperature that would result when a sample of 500 grams of water at 22 degrees surrounds 0.5 grams of solid graphite reacting with an excess of hydrogen gas in a metal chamber. Assume the heat capacity of the container is that's a tough word to say. Negligible. Okay? All right, so it's definitely a calorimetry problem. So it's talking about temperature and, water being involved. But what strikes me as most important is this guy right here. Okay? 0.5 grams of the graphite solid. Okay? If I go back up here, this whole reaction that I wrote, that I calculated delta H formation, was for 2 moles of graphite reacting with hydrogen. Okay, would require 226.6 kilojoules. Okay? Well, for this process, I only have 1/2 gram of graphite. So, you know what? I'm not going to need 226 kilojoules of energy to do that. So the first thing I see here is that we need to do a little stoichiometry. I need to take that 0.5 grams of carbon and say, okay, how many moles is that? Okay, and then from there say, okay, according to this equation that we wrote here, with graphite reacting with hydrogen, for every 2 moles of carbon in the form of graphite, 226.6 kilojoules of energy would be required to react with that hydrogen to make the acetylene. Okay, so when I calculate that through, I'm also going to go ahead and convert that from kilojoules to joules. That comes out to about 4,717 joules. Okay, so that's the amount of energy that would be released for this process that I'm describing. That's such an important step to recognize that. Okay, now in calorimetry world, okay, you better start thinking about Qs. So let's see, this is the amount of energy released according to my chemical reaction taking place here. So I'm going to go ahead and call that Q of reaction. That's the amount of energy absorbed in this case by my chemical reaction using 0.5 grams of graphite. Okay, well, let's see. Calorimetry experiment. It's asking me about the final temperature of the water. Okay, so with that in mind, let's see here. The heat absorbed by the reaction, where did it get that energy from? Well, it stole that energy from somewhere, its surroundings, which in this case is going to be the water in this, surrounding this metal chamber. So the heat absorbed by the reaction is going to equal the Q lost by the water. Of course, the only difference between these two Q values, heat gained equals heat lost. They're going to be the same numeric value, but opposite sign. Okay? So therefore, my Q of water is going to be negative 4,717 joules. Okay? Now, I can start dealing with the calorimetry part. So the M times the C times the change in T. Okay? So let's see here. My mass of water, well, in this case, 500 grams of water. Okay, now if you guys were doing a solution, it would be the mass of water plus the stuff you're dissolving. If you were doing a chemical reaction where you're mixing two solutions, like 100 mils of this and 100 mils of that, you'd add that together to get the total 200 mils. But for our case, it's just 500 grams of water. Specific heat of water. And I'm just going to go ahead and solve for the temperature change. Now notice it says the heat capacity of the container is negligible, so I don't have to worry about adding, any heat lost by the calorimeter itself or the container. All right, so that's pretty solvable. So I'm going to go ahead and calculate for delta T. And it should come out to about like a negative 2.25 degrees-ish, okay? So what does that mean? Is the temperature of my water going to go up, or is the temperature of my water going to go down? Well, because the process was endothermic, it absorbed energy, it took energy from the surrounding water, so the temperature of the water is going to go down. So let's see, my T final, well, my temperature started at 22 degrees. Whoops. So it's going to go down by 2.25 degrees. Okay? So taking into account the sig figs, we're going to be looking at around a final temperature of 19.7 degrees Celsius. Okay? So that's kind of an interesting application, okay, with calorimetry. The most important part was you got to know when to apply the stoichiometry. Okay, remember, delta H values, no matter if they're delta H formation, delta H of combustion, or delta H of reaction, is going to be usually kilojoules per mole or kilojoules per the balanced equation. Okay, so it's going to be a per mole scale, whereas when you got to do stoichiometry, that's when you're using any old random amount. Okay, and you have to adjust it. Okay? All right, well, that was fun. Last but not least, standard heats of formation. Okay, so this was another way that you can calculate delta H. This is a guy where, it's not Hess's law. I don't have a whole bunch of reactions to work with, but yet in the problem, it's giving me all these delta H's of formation, okay? So this is the formula where your delta H of reaction can be calculated from standard heats of formation, but it's the sum of the delta H of formation for the products minus the sum of the delta H of formation for the reactants. Okay, so in this problem, though, it's got a little twist. All kinds of numbers here. It says calculate the standard enthalpy of formation, okay, for dinitrogen tetrahydride, N2H4. So that's this guy right here. When the standard enthalpy of reaction for the following reaction is negative 337 kilojoules. It also tells me the standard enthalpy of formation for NH3 is negative 46. Okay, so, this one's kind of twisty because it gave me the delta H of reaction. So guess what? It gave me this number, okay? I have the delta H of formation for the NH3, and I'm looking for the delta H of formation for this guy, okay? So it's a little bit different. So I'm going to go ahead and pop in the negative 337 kilojoules, okay? And then heats of formation of the products. So products minus reactants. So when I do that, let's see here. We're going to have 4, because there's 4 moles of NH3, times the delta H of formation of NH3, okay? And then, okay, our other product, the nitrogen. Well, what's the heat of formation for nitrogen, an element in its most stable form? 0. Please remember that, okay? Heats of formation of an element just sitting there by itself is 0. Minus, okay, the heats of formation of the reactants. So let's see here. 3, because there's 3 of them, delta H of formation of the N2H4. Okay, so now we can calculate. So negative 337 kilojoules, and then we'll plug in some values. So 4 times, this number was given. So go up here, negative 46 kilojoules per mole, but the mole is going to cancel out with these 4 moles here. So I'll just drop it off. Don't care about this. And then minus 3, and this is basically what I'm looking for. So I'll call that X. How's that sound? Okay, from here it's a matter of solving. Got to be really careful with your signs. This is a negative 46 times 4, so it's going to be a negative value. So when you take it to the other side, you're going to have to add it. Okay, so when you add 4 times 46, it comes out to a negative 153. okay, and then equals a negative 3 times x. So that's how it simplifies a little further. And then we're going to divide both sides by negative 3, divide both sides by negative 3, and x comes out to 51 kilojoules per mole. And that would be the delta H of formation standard for the N2H4. Okay, so that's kind of a fun problem. Again, that's sort of unusual because most delta H of formation are negative because heat's released when you make that compound, but not always. Okay, so this is a positive delta H of formation for that compound. Okay, so kind of a twisty question. Otherwise, these are usually pretty traditional. If I give you a bunch of delta, our standard enthalpy of formation, a bunch of delta H with a little f, you know, typically just plug them in, products minus reactants, and you're good to go. Okay. All right, well, I hope this has helped. You know, it just gives you a resource to look back on. But otherwise, thanks for listening. And if you have questions, please don't hesitate to come in, get some help. Thanks a lot. Bye.